Okay, right now what I wanted to do was to spend a little time in this video explaining in some deeper detail some stuff about the net change theorem. Okay, so the net change theorem is a pretty simple form. Okay, it's often written as f of b equals f of a plus the antiderivative, or the integral, from a to b of f prime of x dx. Okay. Now, this is a direct consequence from essentially the fundamental theorem of calculus part 2. If we look at it like this, remember the statement says that if this function that's listed right here and here is the antiderivative of this function that's listed here, then from a to b, this is going to be the answer. Now, big F is clearly the antiderivative of f prime, that's by definition. And so then I've got my upper bound and my lower bound, so hooray. So this is, remember, the fundamental theorem of calculus part 2. Okay, and this is the so-called net change theorem, which is essentially, in my opinion, it's the exact same thing. Okay. Now, what I wanted to do was explain this a little bit more in terms of like application. What does it mean? Less about like mathematical definition, because the form that this takes is a bit different than this, where this guy is often written with the lowercase f there, and it says where big F is the antiderivative of little f. Okay, so to try to explain this a little bit more, okay, I want you to pretend that we just know sort of two pieces of information. Okay, I know where a function starts, f of a, and I know information about its derivative. Okay, so this is, we're going to interpret that as my starting point. And then this guy right here is like, how does f change? Flow is another good word. Move is another good word. Okay, so to get this sort of pictorially, all right, I'm going to make this my x-axis. And let's say there's a point A right here. Okay, so my known information so far is I know this point right here where that y coordinate is f of a. All right. Now, if I know the derivative at any value of x, then I know the derivative at point A, right? I could calculate whatever that quantity is. And what that would give me at this point right here is some sort of instantaneous rate of change, or the direction that f wants to move in after this point. Does that kind of make sense? And so what I could do, and this leads to a lot of like numerical methods for doing stuff, but is I have a point right here. Now, remember, this is instantaneous. Okay? And what I've done right here is a little something of an approximation. I've let, oops, I didn't mean to write that, a plus h right there. I said after moving about h laterally, this is roughly how far I will go up. It's an approximation. And so I get this approximation like f of a plus h. So far, so good. It's exactly equal to, first off, by essentially the fundamental theorem of calculus part 2, a to a plus h, big F prime of x dx. Okay? But what I'm going to assert right here is this is roughly equal to where do I start plus how long do I wait, or how far do I go horizontally, multiplied by what is that rate of change supposed to be, in what direction am I pointing it. Does this kind of make sense? And I want to use this approximation for that as our way to try to understand a little bit about what's going on with the net change theorem. And it comes in play later in classes like differential equation and numerical analysis and things like that. So it's quite fun. Okay, so bear with me for a second. Okay, But now what this tells me I can do is I can kind of roughly sketch out these paths. That kind of makes sense, where I'm doing all these sort of approximations with straight lines. So it's not exactly the curve or whatever that f is going to take, but I can do all these little approximations step by step by step by understanding that where am I later? Well, where did I start? How long am I moving? And in what direction am I moving in? That's the way that we kind of want to understand this approximation. And this guy right here is basically like the perfect amalgamation of that, okay? This bad boy right here is in a very real way, it is totaling movement with direction over a to a plus h. Okay, I want us to understand that idea, okay? Because there are some basic words that I want to use when I talk about the net change theorem. Okay, so if this kind of makes sense, this approximation is roughly where do I start, plus how long do I wait, plus what direction am I, or times what direction am I moving in. Great, move on. If not, pause, rewind the video, rewatch it, try to understand that sort of like plain language interpreting the approximation and then using that as a way to understand the right answer. Okay? I'll be erasing while you're deciding what to do. Okay. Now I'm going to write this with that plain language so that we don't forget. Okay? Where am I? Okay. Well, where did I start? Okay. How long have I been moving? In what direction? Well, how long have I been moving? Sorry. In this direction. Okay. So where am I? Well, where did I start? And, sorry, forgot the word and there. How long have I been moving in this direction? Now, the this here, this guy can change, so the direction can be going any which way. Okay. The how long have I been moving? Okay. This puts a little bit of meaning into f and x that we don't want to say is true all the time. Okay. This long is basically it's implying that x is like time, which is not always true. Okay, but this is a good analogy. And it also means that f is location, which again, not always true, but is useful in this analogy. Okay, let's solve a problem using the idea of the net change theorem now that we understand it completely. Okay, so I want to consider a leaky bucket. All right, so let's draw a bucket. I got a bucket that I've made. I'm making this bucket way too big. Let's make the bucket over here. Okay. So I've got a bucket. Okay. And it's got a hole in it. Boop, boop. Okay. Now the bucket has some fluid in it. And I'm going to say that the height of the fluid in my bucket is described by h of t. Okay. Now there is water coming out. Right? And I'm going to assert that it's coming out at a particular rate. I wrote my rate down here somewhere. Where did I put it? There it is. It's flowing out at a rate of, I'm just going to drag this over here so I have it. G times T minus the square root of 2gh0. Okay, so let's understand what these things are here. This is gravity, so we're just going to use like 9.8 meters per second squared. Okay, and then this guy right here is the initial height of the fluid. Okay, so we can see at time 0, this term vanishes, and we just have this pure term right here dragging water out at a particular rate. Then as time goes on, this term gets bigger, and so the outflow, we know it's out because it's negative, starts to decrease. So this quantity increases, so my flow goes closer to 0. Okay, so I'm losing like less and less per unit time as we go on. Kind of makes sense? Okay. So now what I'd like to know is, hey, let's take any time t at time, let's call it big T. Okay. What is the height of fluid? That's our blue stuff in the bucket. Okay. So if I set this up, I'm looking at, well, what is V of t? Okay. Now, what is the information we know? Not V of t, silly goose. H of t. Okay. So what do we know? We know how the flow changes over time, or the height changes over time. It's according to this formula. And we know the height at which it started. No. All right. So since we know a rate and we know an initial point, that's the net change theorem. Bing, 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 bing. Especially since we're trying to find what is the height at a particular time. So I'm going to stand up. H of t is equivalent to where did I start and for how long have we been waiting, or how long have we been moving in this direction. Make sense? Now, you should be able to solve a point of view. You should be able to solve this by this point, but if we can't, we just should recognize it as a polynomial. This is a linear part, and this is just a constant. So it's going to equal where I started plus g over 2 t squared. I'm going to go ahead and put a parenthesis right here. Minus the square root of 2gh0 t. And then we're evaluating this from t equals 0 to big T. Okay? And so what we arrive at is the initial height plus g over 2 big T squared minus 2gh0 big T. Reconcile to yourself on why that's it and I don't need anything else. Okay? I hope this helps a little bit with understanding the net change theorem and seeing it in action a little bit. Okay? That's going to end it for now. Where's my stop recording button?